Ladies and gentlemen, and welcome to Cloud Connect on the second day. I again would like to thank all the people out here, and it's really a pleasure and privilege to have such a distinguished gathering of attendees and speakers alike. So we start off the day with Mr. Jason Bloomberg, President, ZapThink. And he's going to talk on architecting a RESTful cloud, the key to elasticity. Mr. Bloomberg is president of ZapThink, a Dovell Technologies company. He is a thought leader in the areas of enterprise architecture, service-oriented architecture, and cloud computing, and helps organizations around the world better leverage their IT resources to meet challenging business needs. Cloud environments are inherently partition tolerant, which impacts both data consistency and application state. As a result, architects must utilize different approaches from traditional application environments, instead leveraging best practices of creating hypermedia applications. In particular, they must move application state off the server to the client following an architectural style known as representational state transfer, or REST. Attendees of this session will obtain an understanding of the unique architectural requirements for cloud-based applications, gain a new perspective on how the cloud can transport and complement existing applications, learn how REST is essential for achieving elasticity in cloud-based applications. Please come in.
Thank you very much. Very good. Well, it's great to be here in Bangalore again. My name is Jason Bloomberg. I'm president of ZapThink. And we're an advisory and training firm. We've been running classes now for several years, including here in India. I've run our service-oriented architecture, a 4-day licensed ZapThink architect course here in other cities in India a few times, and recently ran our cloud computing course as well. We have a 2-day cloud computing course, and ran that in Bangalore actually just a few months ago. We had 150 people. So it's anybody here has been in one of my classes before? All right. Excellent, very good. So got some fans in the audience. So I wasn't able to come to this conference yesterday, but I showed up for the first 2 keynotes today. I found them a little thin on technical content. So I'm wondering, whenever I go to these cloud conferences, sometimes it's more business, more technical. So how many of you would consider yourself more on the business side? One poor guy. Okay, so how many of you would consider yourself more on the technical side? Okay, everybody. Right. That's what I was figuring. India. So what do you think? Do you think that there's a sufficient technical depth so far in this conference? Okay. Well, hopefully we'll fix that. I'll only have half an hour, but I'll do my best. So what we'll be talking about is architecting a RESTful cloud, the key to elasticity. So this talk is aimed at the architects or people who want to think like architects. So if you're a developer, it's still quite relevant because it's the broader context of building applications. So that hopefully that'll be useful. Okay, so let's start. We're in an enterprise environment, right? Large organization, so we have a lot of existing applications, legacy applications, and they look like this, right? Anybody have one of these or a bunch of these? Spaghetti code, right? Some sort of ancient thing that's on some old piece of technology, and it's a bunch of spaghetti. You've lost the source code, or people have been tweaking the source code for 25 years. Nobody knows how the thing works anymore. Sound familiar? Okay. Now along comes the boss, and the boss says, "Ooh, cloud computing. Let's move this to the cloud." Okay. So now watch closely. We're going to move this to the cloud. Okay, ready? There we are. That's what the boss wants, right? Wants to put all that spaghetti code in the cloud. Well, it's not going to work like that, especially with some of these older applications. There's a lot of talk about the value of migrating legacy to the cloud, and yeah, there's a lot of value there, but it's nowhere near this simple, right? There's a lot more to it than that, so we'll talk a bit about that. Okay, let's say it's not quite that bad. Let's say it's not ancient spaghetti code. It's some sort of modern distributed application written in Java or C#, right? It follows all the OO best practices, and now the boss comes along and says, let's move that to the cloud. Okay, so now watch closely. Let's move to the cloud. There we are. Well, even with a modern distributed application, there's still important considerations. It's not this simple. You can't just pick up that Java app, stick it in the cloud, and expect to get the benefits of the cloud. And that's the challenge. What do we need to do to our applications to architect them for the cloud? So the key essential characteristics of cloud computing that are the most difficult to achieve are elasticity and fault tolerance. Now, elasticity is perhaps the most important of all, right? The ability to scale up as needed in an on-demand, automated way, and then scale back down as needed when you don't need the resources. That's a critical part of what it means to do cloud computing. If you don't have that, you don't really have cloud, right? You might have virtualization in a hosted data center, but what's the difference between that and cloud? Well, it's the elasticity, right? And that is difficult to achieve, and once you achieve it, you have to think about how your applications can take advantage of it. Now, fault tolerance as well is critically important. Not that it wasn't important before, but the cloud handles it in a different way, right? Instead of trying to build very highly available systems, the cloud basically says, well, availability is less important. If a particular box or virtual machine goes down, we'll have an automated way of reprovisioning it. So you'll bootstrap a replacement dynamically, and we'll be up and running. So it's not that we're keeping things from going down, it's that we have an automated way to recover from failure. And that's a new way of looking at fault tolerance. Well, if your application isn't designed for that, you're not going to achieve the benefits of that either. So how do we need to think about our application to achieve these benefits? Well, the focus here is rapid elasticity. So this is a slide from NIST, and NIST is a U.S. government-sponsored standards body that has really helped define cloud computing for the world, really. It's more than just the U.S. And so this is basically their deployment models, service models, and among the essential characteristics, rapid elasticity. That's essential. If you're not doing that, you're not getting the benefits of the cloud. So, what do we mean by elasticity? Well, it's rapid, it's automated, and it goes both up and down. So if you think elasticity means, oh, I need a new virtual machine, so you give your sysadmin a call, and 6 days later, they call you back and say, oh, that virtual machine's provisioned, that's not elastic, right? Elastic means automated and rapid. Now, how rapid is rapid depends upon the physical constraints, right? Obviously, if you're going to be configuring an entire, Linux virtual machine, it might take 45 minutes or an hour, and that still qualifies as rapid. It's definitely not a week, though, right? So how many instances are you going to have? And when I say instance, it could mean an application instance, a virtual machine instance, a database instance, storage instance, right? There's many different kinds of resources that we're abstracting in the cloud computing environment. So how many of those are we going to have? Well, we don't know. We don't know ahead of time how many instances we're going to need. This is part of the challenge of elasticity. With a traditional distributed application, you do your traditional capacity planning, you'll have some idea how many servers you're going to need. And yeah, you might need to add more if your capacity needs change, but that's typically done generally in a manual way. Cloud computing, we're saying, well, we don't have to know ahead of time because we're elastic. If we need more resources, we'll just provision those automatically. So we have to architect our application without knowing how many instances, application tier or database tier instances, we're running on. That's a new way of thinking about how we're going to design our distributed application. Another key challenge is how we deal with state information. Right? Let's say we have a stateful application. Now, not every application is stateful, but any application that has to keep track of users or keep track of processes is going to be inherently stateful. So the example I like to use is our friend e-commerce application, right? The shopping cart. You go onto some shopping cart website, and every user has their own shopping cart, and every shopping cart's in a particular state at a particular time. So that's a classic example of a stateful application, but really any number of applications fall into this category. So where are we going to maintain that state information for each of these individual users or customers? Well, if we maintain it on the cloud instance, that is the application tier instance that is actually running the application, we're going to have a problem because that's not fault tolerant, right? Because that instance goes down, we lose that state information. So we don't want to put it there. So where else can we put it? Well, we could put it on the persistence tier, right, on the database tier. So every time any of our users clicks a link, we write that information to the database. Click a link, write to the database. Click a link, write to the database. Well, that doesn't scale very well, right? That's essentially a two-tier application, and if you've ever used a two-tier app, right, you can only support so many users, so many concurrent sessions, and then you have to start dealing with how to scale that. So that's not going to work for us either. So we could push that information to the client and maintain application state in the client. Well, traditional ways of doing this, like setting a cookie, well, we can set cookies, but people can turn them off, and people can delete them. Nobody likes cookies, right? And cookies are HTTP specific, so if we're in a non-HTTP environment, we can't use them anyway. So that's not a very good answer either. What we need is an architectural approach that enables us to leverage application state on the client in a way that meets our needs and allows us to be elastic and fault tolerant. So essentially what we want to do is we want to enable hypermedia to be our application state engine. So hypermedia, essentially we have a big website. Only it's not just web pages, it could be any kind of media. So it could be XML files, JSON files, media files, any kind of file, interconnected via hyperlinks, and that's our application. Right, so we're building a distributed hypermedia application, and we want to enable that hypermedia application to maintain the application state for us. So where is the user in that shopping cart? Well, it depends upon what page they're on and what links they can click. So you're familiar with state machines, right? Every user is in a particular state. And shame on you. And every state has transitions, valid transitions to other states. And so clearly clicking hyperlinks is a great way of navigating a state machine. So that's what we mean by hypermedia as the engine of application state. Now that phrase, hypermedia as the engine of application state, that also goes by the acronym HADOS, and it's one of the 4 REST constraints. And it's the one that developers usually don't get. So when we talk about REST, we'll define it in a moment. We talk about 4 constraints, and HADOS constraint is the one that people usually don't understand. But it's the most central, most important one, because REST is all about building distributed hypermedia applications. And this is going to be how we're going to deal with state as well as elasticity informations in a cloud computing environment. So how does this work? Well, the web pages or the representations, which could be any media type, essentially reflect the current state of the app through hypermedia, right? Through this, where the particular user is and what links they can click on. And those links essentially have opaque references to any state that the server has to keep track of. So not all state information is on the client. That's the application state that is specific to each user. Resource state is state information that everybody shares. So that e-commerce application, it has to keep track of how many of a particular book or inventory. Well, that inventory number is something everybody has to share. That's part of the resource state. Well, that's handled behind the scenes, right? So that anybody who is having a shopping cart, they click a link, and the link will either put that book in their shopping cart or click a page saying that that book is not available, and what's going on behind the scenes is hidden from view. Okay, so HADOS, right? It's one of the 4 RESTful constraints, and if you're a Restafarian, if you're familiar with REST, then you're probably familiar with this, but it's also the one that developers struggle with. But it's the point of REST. REST is about building hypermedia applications by transferring application state to the client. This is what we mean by representational state transfer. So why does REST have that goofy name, representational state transfer? Everybody ever use REST and wonder what the hell's the name about? Well, that's just what it's about. We're transferring application state to the client in the form of representations. This is how we do what REST is. We move the application state, and that's what it's about, transferring application state. Okay, so what is REST anyway? Well, it was invented by this guy, Roy Fielding, in his doctoral dissertation. So Roy Fielding was one of the creators of HTTP. So he's one of the founders of the web, essentially. And then when it came time to do his doctoral dissertation, basically what he did is he looked at the web and saw that it was good. Ooh, yes, the web is good. By 2000, right, the web was already immense. It's resilient, right? You can't take down the whole web. You can have a web server go down here or there, but the overall web keeps running, right? And it keeps growing. It's infinitely scalable, and nobody is in control of it. Right? There's no one person running the web. We each run our own web servers or whatever, so we have millions and millions and millions of people controlling it. Nobody is in charge of the thing. So he looked at the web and said, wouldn't it be great if we could distill the architectural principles that make the web so special into a set of abstracted constraints that we could apply to software in general. And that's what REST is. So it's not coming up with these sort of academic constraints and saying, oh look, the web happens to follow them. It's the other way around. Looking at the web and saying, wouldn't it be great if we could apply those principles to software in general? And that's essentially what it is. So, okay. So when we talk about REST, we have some essential terminology. It'd be great if I had more than half an hour. I could go into more depth. But we talk about resources. That's essentially some capability on a network. So it could be a web server that delivers you a web page. Or it could be a PHP script that can build a web page for you dynamically. Or some other media representation like a JSON file or an image file or something else. Representation is what that resource gives you. It's the manifestation of the resource. And these are different things, right? The PHP script on the web server and the web page it builds look very different, right? And if you're looking at that web page, you don't see the PHP script. But the PHP script is what builds the web page for you. And we use the term hypermedia, which is essentially an update of the old term hypertext, as in hypertext transfer protocol, which were pages interconnected by links. But now it's not just text anymore. It's many different types of media. Okay, so REST, if you're doing REST, what that means, it's an architectural style, which means you have to follow a core set of architectural constraints. And REST defines 4 of them. If you're doing these 4, you're doing REST. If you're not doing all 4, maybe doing something that's similar to REST, but you're not doing REST. So what are the constraints? Separation of resource from representation, manipulation of resources by representation, self-descriptive messages, and hypermedia as the engine of application state, the dreaded HADOS. Okay, so there's no rule that says you have to do all 4. The rule is, if you want to be doing REST, you have to do all 4. But what is REST for? Building distributed hypermedia applications. If that's not what you're building, then REST may not be the best approach. But if that's what you want to do, you have to follow all 4. Okay, so I'll talk, in the longer presentation I have a slide on each of these, but since I don't, I'll just briefly introduce them. So, separation of resource from representation. Right? The PHP script and the web file web page generates are different. We're separating those. And the servers keep track of all of those resources, and how they work is transparent to the user. Manipulation of resources by representations. How do we tell the server what to do? Well, we have a web page and we click on links, we submit forms, we do the things that we can do in our representation, whether it's a web page or any XML file, JSON file, whatever representation that we have. That's how we interact with the server, is by clicking links and doing the get, post, put, and delete operations that are part of the REST interface. Self-descriptive messages, right? If we need metadata to tell us how to process a representation, it will be in the representation. Typically in the form of a media type. This is an HTML file that tells your browser, make it look, process it like XML or HTML. Or this is an XML file, here's the schema, go fetch the schema. Or this is some other kind of file. That information is included in the message. And then, of course, HADOS. Okay. So what does HADOS mean in action? Well, the hyperlinks describe the contract between the client and the server in the form of a workflow at runtime. So how do this client and server know how to interact with each other? Because the client can click hyperlinks, and that forms a runtime workflow. So runtime workflow, that word workflow, should ring some bells, because that essentially describes a business process. But now it's no longer a design time workflow where we figure out how the process has to work ahead of time. It's a runtime workflow, because the links can be generated as dynamically as we want them to be. So when we're working on code on the resources, which is where we do all the heavy lifting, we can build hyperlinks any way we like. So that each user clicks different links, or each time they come to a particular website, there are different links at different times. However, we have whatever level of flexibility we require. Okay. So how does this, let's tie this back now to the cloud story. How does this deal with cloud? Well, here's your app before the cloud, right? Traditional n-tier application, we have our database or persistence tier, we have our application tier, we have our client tier. Okay, so how does this work? Well, we have traditional ways of handling scalability, right? On the database tier, we have sharding, data virtualization, other approaches, traditional ways of handling scalability, often through vertical scalability approaches, where we put more processors in there, we build these tightly coupled Oracle clusters or whatever we need to do. Middle tier, we can do clustering there as well, so we can do application server clustering to scale that. We can use load balancers, and we've figured out how to do this, right? Traditional n-tier applications, this is how you can build an eBay, right? It works pretty well. We know how to make it as scalable as we need it to be. And how do we handle state information in a traditional n-tier application? Well, we can write persistent state to the database, but that we only want to use a very light touch, because if every time somebody clicks a link, it doesn't scale very well. So we only want to put state information that we really need to share across different users. So how do we typically do it then? We use the middle tier. Session beans, threads, server cookies, right? Various techniques for maintaining application state on the middle tier in our application servers, in our ESBs. That's the traditional approach, right? So you're probably familiar with that. You've probably done that yourself. You spawn some sort of instance in the middle tier, typically a thread, or a server cookie that now represents that session. And that's the traditional approach. Now we can use cookies, but as I said, we can't rely on those because people can turn them off. And it depends upon browsers, it depends upon HTTP. Right? So cookies are of limited use. Okay. So what about the cloud? Well, in the cloud, we don't know how many instances we're going to have. Right? So it's elastic. So what we want to make sure of is we want to make sure this middle tier is stateless, because we don't want a particular instance to have any state information on it, because that might go down, or we might need to spawn new instances to provide greater scalability. So we want to make sure there's no state information here. So we push some state information down here, but only the resource state that's shared for everybody. The challenge here is pushing the application state to the client. But remember, that's why we call REST, representational state transfer. Transfer application state in representations to the client. So here's how it works. Here's the user, right? Using a shopping cart. So this user, she comes to the Amazon.com website, right? Wants a shopping cart. Now, if you've ever been to Amazon, you know that they maintain your shopping cart information indefinitely. Right? You can put something in your shopping cart, come back 10 years later, there it is. It's out of stock and the price is doubled, but it's still in your cart, right? Because Amazon does that for you. They maintain that shopping cart state as part of the resource state. That's obviously written to a database somewhere. Come back 10 years from now, how else could they do it, right? So, user comes back to the shopping cart, and what does the backend do? It spawns a cloud instance to handle the shopping cart or the e-commerce application for the course of this session. And the backend puts a hypermedia representations of that cart application on this middle tier instance that it spawned for this purpose. Or potentially there's one already instantiated, and if there's room for it, it might put it on an existing one. It doesn't really make any difference. But that hypermedia application is essentially all of the underlying code in the resources that will run the shopping cart application. But it's inherently stateless, right? It's the same application for everybody. Okay, so now that running on the middle tier serves up the web pages. Now here's your cart, and the user sees the shopping cart application the way she is expecting, and here's the happy path, right? Everything's working fine. Click link, submit forms as she navigates through the shopping cart, and if nothing goes wrong, then everything's fine. Now let's say we need to scale that middle tier. The Amazon, of course, has thousands and thousands of customers at any point in time, so the middle tier provisions a new instance dynamically in an automated fashion. Remember, that's what elasticity means. If I'm running out of capacity, or for whatever reason, I can spawn a new instance, that's fine. Well, there's no problem because those instances are stateless. So it doesn't matter which of these instances is serving these requests, because all the information about where the user is within the hypermedia application in the form of stuff in the URL and hidden form fields, etc. Okay, so the happy path, she completes her transaction, and at the end, of course, we have to update the resource state. That's executing the credit card transaction, fetching the book out of inventory, whatever we need to do. But let's say something goes wrong. Okay, here we are. Bam, instance crashes. So in the middle of the session, a cloud instance crashes. Well, in a traditional environment, we have problems because we'll lose some state information. So the customer now doesn't know if the process is complete, if a card has been charged, right? And this is a bad situation. But in the cloud, how do we deal with this? We spawn a new instance, put it back into production, and continue on our way. And because that instance did not have any state information on it, it doesn't matter which instance serves the requests. So this is essentially how we need to work these things. Right? If we don't do this, if we maintain any state information on any sort of cloud instance where we want it to be elastic, we're going to have this problem. All right. So she continues based on hyperlinks. All the state information is maintained, and everything's fine. All right. So there's more to this story. I mean, I can only cover so much in half an hour. Right? I can't tell you if this is the right approach for your application. This is talking about a particular class of stateful application that requires high levels of scalability and elasticity. That may not apply to you. Right? There's other kinds of applications. There's other sorts of scalability and elasticity challenges. So you have to understand, this is one of the challenges of the architect, based upon the business problem at hand, what is the right approach for you? So we went through one kind of approach for dealing with one class of problem. But I'm not saying this is necessarily your problem. So you have to understand which cloud deployment options are right for you. And this is a key thing to keep in mind for the rest of the day as well. Cloud means a lot of different things, right? It's not just one kind of resource. It doesn't solve just one kind of problem. So it can be a challenge for a conference like this, saying what is cloud? Well, cloud is a lot of different things because there's a lot of different problems and a lot of different tools and technologies we can bring to bear. Bottom line, you don't know cloud is the answer unless you know the question. All right, well, that's it for my talk. So, questions? Yes?
You were talking about moving the application state to the client. That inherently brings a lot of security issues, right?
That is always the first question. So, and you're not a plant, but that's good. Obviously, if we're putting any information on the client, there's the obvious security question. What if it's a bad actor, some sort of hacker? They take that state information and they monkey with it to try to change the price of the book to 1 rupee, right? And get this big expensive book for 1 rupee. Or maybe they monkey with the state information, session information, to break into somebody else's shopping cart, steal somebody's credit card. That's obviously going to be a question. Well, how do we solve that problem today? Well, we don't. If you look at the hidden session information, whether it's in the URL or hidden form fields today, you won't see, oh, this is cart number 47. Change the number from 47 to 46, and we'll steal somebody else's cart. No, what do you see? You see a bunch of gibberish in there because it uses a hash algorithm and it uses checksums. If a hacker goes in there and monkeys with it, the worst that can happen is they will hose their own session, right? And they will get an error code, and then they're screwed up. That's the worst that can happen, right? So, but that's not a new technology. It's just something we have to bring to bear in order to secure our sessions, so that we don't have those sort of shenanigans. So that's actually how Amazon works. If you view the source, you go in there, you view the source. They use a lot of hidden form fields with a bunch of these hash values in them, and you can go in there if you're a good hacker, which I know probably the entire room is. You can go in there and monkey with that session information. Good luck coming up with some alternate session value that is valid. I mean, good luck with that. Yeah, question?
How do you handle authentication?
Oh, sorry, over here.
How do you handle authentication?
How do I handle authentication? Well, that's a conversation that doesn't fit into this session, but one of the key approaches that is very common now is using OAuth, because OAuth is lightweight and it works well in a stateless environment. But I just don't have the time to go into that today. Yeah?
You're talking about elasticity and you mentioned rapid, automated, measured, reversible. So
Yeah?
what do you mean by reversible?
Well, the reversible is important, right? You want to be able to provision instances if you need more capacity and deprovision them if you don't need the capacity anymore, right? Because otherwise you're not going to save money, right? If you're in a situation, well, I want to provision 12 instances on Amazon and just to do a particular task, and then you just leave them there forever and ever, well, Amazon was perfectly happy to keep sending you the bills forever and ever, and your boss is going to say, well, what's this bill for? But 2 years from now, you're not going to remember. So it's like, well, I don't know if that instance is useful for anything. Better keep it around until the end of time, because if we take it down, who knows, right? So you have to be able to deprovision as rapidly as provision to get the benefits of elasticity. Okay.
Do the browsers need any extensions or anything of that sort to support the RESTful APIs?
The process?
The browser?
The browser? Well, we didn't really get into RESTful APIs. APIs are part of the RESTful story, but are not the whole story. This is where a lot of developers go wrong, is they think that REST is about APIs. And having a uniform interface with get, post, put, and delete simplifies a lot of things, makes it a lot easier to work with REST than, say, web services. But REST is really more about building distributed hypermedia applications. So, in terms of get, post, put, and delete, well, I mean, it depends. If the client is always a browser, then get and post you can take for granted. Put and delete you might not want to use, and there's maybe a few other, but that's a whole different kind of story, right? One of the key things to keep in mind, we're using the terms client and server, but those are abstractions. It's not that we're talking about client-server architecture. It's just that we have a resource on server, and we have something interacting with the resource. We call that a client, but that might also be a server. And traditionally, we do have multiple tiers, and then one of the middle tiers will act as both a server and a client. So don't get too hung up on those words, server and client. Yeah, standing room only. I love it. Over here.
How do you capture and store the hyperstates?
How to capture and store what?
How do you capture and store the hyperstates, the session information?
Well, the browser does that, or the client does that. So if the client is a browser, you let the browser do it. But even if the client is a program in its own right, you can cache that kind of information on the client. So when we talk about RESTful SOA, for example, which is a whole other session as well, we're doing both SOA and REST, well, we focus on intermediaries that abstract underlying capabilities and present RESTful service interfaces, and those essentially can cache information, and that you can cache state information there as well. It depends upon what you're trying to do. So again, that's a whole other conversation. Okay, another question.
So from a developer perspective, is REST just a concept wherein I am embedding everything in the web pages rather than depending on cookies or anything else?
Well, there's more to REST, right? It's not just the APIs and it's not just the web pages. It's partly how you think about building these hypermedia applications. Because keep in mind, a hypermedia application doesn't even necessarily have a single point of control, which is a different way of thinking about applications. Right? In the enterprise context, you have SAP, you better believe somebody's running that thing. Right? There's obviously a single point of control. Well, hypermedia applications, the hyperlinks can link to other servers, and you don't necessarily have that. So it's a different way of thinking about building an application. So one of the key RESTful ways of thinking is that self-descriptive messages constraint. Right? If your client needs to know what to do, it should be able to ask the server for instructions in the form of metadata. So the client can say, well, what can you do for me? And the server should be able to say, well, I can give you XML or JSON or HTML, and then based upon that information, the client may make a choice. Or the client might say, well, okay, you can give me XML. Well, what kind of, how do I format my data? Well, and then you can request the schema if that's appropriate. Or if you're using a different media type, then you can request other metadata. So this is part of the challenge as well, is how do we set up these interactions? Now, browsers don't necessarily support all that. It's not like a browser can say, well, what kind of media types can you give me, and then select one off of a list. We don't expect browsers to do that. But if the client is supporting some sort of application that you're building, right, on a device, then you can program that application to do any sort of introspection to any sort of resource. And this is how we achieve, long-lasting loose coupling over time. If the client knows it can ask the resource for any information about what it can do for you, then the resource is now flexible enough to change what it does. You can add new capabilities. And the client should be smart enough to say, well, what can you do for me now?
Just one more thing. So another thing is, do you really feel that we need to give extra consideration to security whenever we are dealing with RESTful applications?
Well, when you say extra consideration for security, that sort of implies that you're not giving security enough consideration to begin with, and that isn't necessarily the case. You always have to consider security no matter what, right?
No,
so whether it's extra, that just means you're screwing something up before.
Mm-hmm. No. The thing is, say, for example, if I have an application already on the browser, browser will definitely, there are definitely pros and cons of doing things via the browser. Like cookies are definitely people don't like, some of them don't like, some of them really use it for some of the aspects. So this is what would be lacking if I go in for a RESTful based thing. I can have an application which would mimic a browser and may not be exactly a browser, right? So the things and all which are supplied by the browser will not be available for the RESTful things.
Well, you obviously have to think about that. But there are technologies as well as standards in place that can solve that problem. One of the challenges of REST is we don't have a rigorous framework of security standards like we have with web services. But on the other hand, we do have a number of security standards, including some of the web services security standards. We can use WS Security and WS Security Policy, some of the others, WS Policy in the context of REST. SAML is in addition to OAuth, and there's a number of others. But it's up to the developer or the architects working with the developers to say, well, how am I going to put these together? When you start working in a cloud environment, that introduces additional challenges. Typically less about threat prevention, although that's important in the cloud, obviously, more about authentication and authorization. Because the cloud provider in a public cloud environment isn't going to give you sufficient granularity of control. Right? You're not going to let the cloud provider manage all your identities for you in the enterprise context where you have existing identity management. Now, if you're a startup, yeah, do everything in the cloud because you don't have any Active Directory, you don't have any LDAP to start with. But if you're an enterprise, you have all that stuff, and now you need to federate that with the cloud because you want to control access control to the cloud locally. That's now where a lot of organizations are currently struggling. But that all ties into the REST story as well, because how are you going to interact with the cloud at that level? You're typically going to do it over HTTP using RESTful calls.
Thanks, Jason.
Haven't gotten the hook yet. Go ahead.
So one of the cornerstones of the whole cloud infrastructure and concept is to move as much application intelligence and state and everything to the cloud and make the client as thin as possible. I mean, that's what we have been hearing. Okay. So this concept, what you're saying.
Well, maybe not. Yeah. It depends on what you mean by the client, and it depends upon what we mean by intelligence. Right? We can put application intelligence in the cloud without maintaining state information in the middle tier, the application tier. We want to let the persistence tier, which we're putting in the cloud as well, maintain persistent information, but we also need to be able to rely upon clients as well. This is an important part of the story, which again is a bit out of, we're changing over to the next session here, this is a bit out of scope for this talk, is if we look at the clients, well, they're not just browsers on computers. They're any number of different kinds of devices. They're mobile devices, they're the Internet of Things, they could be automobiles or refrigerators or factory equipment or air conditioners, right? And all of these are not just clients in the sense that they are thin interfaces, they may be part of the cloud itself. There's nothing in the definition of cloud that says that all of your resources have to run in data centers, right? In fact, the word ubiquitous is part of the definition, right? Cloud is a ubiquitous set of provisionable resources. Those could be mobile devices or factory equipment. And now we're putting intelligence in a distributed way, not just in the data center, but anywhere we want to put it. And now the challenge becomes, how do we manage that? How do we secure that? How do we control that? But that's a huge part of what's going on today. And that's one of the challenges the enterprise has, is people are using these mobile phones for a whole lot of stuff that is not managed, and they don't know how to manage it. Right? But that mobile phone you have in your pocket today is more powerful than the most powerful supercomputer from 20 years ago. Right? It sort of boggles the mind if you think about it. So if everybody has a supercomputer in your pocket, why would the enterprise want you to use PeopleSoft? It's like, who the hell wants to use PeopleSoft? Right? If you can get everything you need on your phone. And that's where a lot of organizations are stuck. But if you think about those mobile devices as part of the cloud, where they're elastic, they're provisionable, they're securable, now we have at least a way of thinking about that problem. It's still very early days. But on the other hand, that's where a lot of the challenges are that people like you folks need to help us solve. So it's an opportunity. Can we keep going?
Last question.
One more question. Okay, you're the lucky guy.
We are talking about the REST protocol or API, or is it something like SOAP called we use for the web services?
Well, first of all, remember my comment that APIs is only a small part of the REST story, and a lot of developers make it into the biggest part of the story. But looking at the great thing about the RESTful API is it gives us a uniform interface. And essentially, the operations are predefined for us. One of the big challenges with web services is we have to specify the operations. So we specify them in the WSDL files, and now the SOAP messages, if we decide to use SOAP, which is optional even with web services, now have to conform to the operations as specified in WSDL. Well, that gives us excessive tight coupling, because anytime we want to change the operations, there's only so many things we can do, and now we have this complex versioning challenge that requires sophisticated governance, and that's where a lot of organizations struggle with traditional web services-based SOA. Well, in the RESTful world, you have a uniform interface, so everybody agrees on the same operations. Now, when you build a resource, you simply have to make sure you can respond to each operation. You have to know what a get means, you have to know what a post means, etc. And if you can respond to those, it doesn't now matter what the client is doing. It's up to now the resource to respond to those calls as appropriate. I think that's all we have time for. There's more to be said on that, but we're out of time. Thanks. Thank you very much.
Thank you so much, Jason, for your deep insights. Now, on behalf of UBM, I'd like to present Jason with a small memento as a token of appreciation.
Thank you very much.
Thanks so much.
Thank you.
Very nice.
Oh, thank you. That's cool.